This is Physics 2211 Lab 5, and we're going to be going over the motion of a slinky. Now, we will be observing the bottom of a stretched slinky that is dropped from rest, and we'll take experimental tracker data to extract the actual position over time. And then we'll have a computational model to predict the position over time for two scenarios, and one will have gravity and tension, and another will have gravity and drag. Now, we need to have a Newton's second law to give us the velocity update formula. And with this, we get a final velocity when you input an initial velocity and add a net force divided by mass times the change in time. And in this scenario, we know the net force without drag will be F net equals negative 9.8 times the mass plus the force of tension. And as we will see later, because the bottom of the slinky does not move, we know that the force of tension needs to be opposite the force of gravity. So it will just equal 9.8 times m in order to give zero net force. We also need the position update formula, which gives you the final position when you take the initial position and add the average velocity times time. This is the actual video that analyzes the position over time for the drop slinky. And as you can see here, the bottom of the slinky stays at rest as the spring is as the slinky is compressing. And then once the slinky finally compresses fully, then the slinky finally decides to move towards the ground. This is part of the calculation loop that predicts the actual position over time data. And so we found the average mass of a slinky to be 0.218, and then the initial position and velocity were set to be 0, with a gravitational constant of 9.8, and then we actually found the coefficient of drag to be 40, which is quite large considering it's a slinky. But actually, this is just because the video used is going in slow motion, so the tracker software thinks that the slinky is actually moving a lot slower than it actually is, so it thinks the actual object has a lot more drag as an effect of that. So having the drag coefficient be 40, while normally it would be a lot, in this scenario it actually does make sense. This is part of the calculation loop that updates the position over time, and this part actually does it for when there is no motion. So we take the force of gravity downwards, so negative 9.8 times the mass, and then the force of tension, which should be 9.8 times the mass because there's no movement, so the two need to add up to give zero net force. So that's how we know what the force of tension is. And then when there's no net force, there's no change in velocity, and then when there's no velocity, there's no change in position. This part of the calculation loop is actually once the spring is fully compressed and is now moving, and so we take the two forces to be the force of gravity downwards again, but this time we add the force of drag in, and so we take those two to get our net force and then apply that to the velocity update formula and apply that to the position update formula. And these are the two data sets. The blue line is the experimental data, and the red line is the computational model data. And as you can see, the two are very similar. And this horizontal line at the beginning here represents when the spring is not moving, so there's no change in position over time. And then once the spring compresses roughly here, then you start to get change in position in the negative y direction. Now, why does the position of the bottom of the slinky not move? We already went over this before, but it's to reiterate, it's just because the force of gravity downwards cancels out with the force of tension upwards. So the compression of the spring is equal to the motion it would have traveled downwards. And one way to kind of think about this more, just mentally to help understand it is the theoretical motion it would travel downwards due to gravity. Uh, while it is traveling downwards, is traveling upwards because the spring is compressing at the same exact speed. So you get zero motion, so zero position over time change. Thank you.